see screen.
Okay, that's what we have discussed last day, and we discussed how can we use diodes for the rectification. We have two methods for rectification. There's half wave rectification and full wave rectification. And I think you may have some kind of idea how can we do this for both full wave and half wave rectification. And the disadvantage of with this half wave rectification, we will not have 50% of the waveform to the output. That's 50% reduction is there. But only the advantage there we can see, only we use single diode. The cost is less. But when you consider that the both things, when you come to the middle point, it's a great reduction, great loss, that because we have 50% of the power provided. Okay. Then when it comes to full rectification, that disadvantage is not there. We can transfer everything to the other side. But you know that when we transfer all these power and waveform or whatever the thing to the other side, we have 0.7 volts reduction through across each diode. Then altogether it may be 1.4 volts drop to the other side, to the output side. But if we don't consider that one, we can consider it as 100% transfer to the other side, because both the negative and positive waveforms are there, the half cycles are there at the output. Then that loss is not here. And only the disadvantage here that we have to use 4 diodes. Probably the when we think about the commercial packages, that the commercial commercial in the sense that they have manufactured putting all 4 things together as a single package. We call it a bridge. Diode bridge separately. We can take 4 diodes and we can make a bridge, or you can take a bridge as a single module. Inside that bridge, we have 4 diodes. So the manufacturers they have developed that one also. But anyway, after all these things, I think you can remember that putting all these things together. After doing that one also, you can see the output side, this type of ripple is it's not smooth DC, it's not the continuous DC voltage we can receive after doing the rectification. Then to do the minimization for this one, and to reduce the ripple of the output voltage, we are having a small arrangement here. We put a capacitor to the output of the full wave or half wave rectification voltage. Then you can see like this, with green color trace is the output one. Then with compared to the dotted line, it's a reduction of the ripple. Okay, the ripple voltage can be reduced much more when you increase the capacitance, but it's again compromisation between the power provided to the circuit and the capacity of the capacitor. Okay, here also we can see that one, it's much better when we have the full wave rectification, but we can't increase much more capacitors here. If it is possible to increase the capacitors, that's a great, we can reduce the ripple voltage, but otherwise we cannot do that one. Only the restriction we can see here from this input side, how much of current we can provide. Okay, then this side, I think here this side we have to provide current. Okay, then that current should be sufficient to provide current to this resistor, load, and the capacitor. Okay, if the current is not up to that level, if the current is not sufficient to provide at the same time capacitor charge and this load current, that input side will be damaged. Because of that, we cannot increase much more capacitance here. Okay, at the end we discussed this protection circuit also. That's what so far we have discussed. Okay, anything, any question regarding these sections? That if you have anything here, you can ask that questions now. If you don't have any question, then we can continue from that point. Okay, I'll share a new document, the today class. Okay, we can start from this point. Actually, that we have up to this point, what was the thing that we have considered? That we have discussed diode applications. Okay, we can use diode as a switch, and the other application is we can use diode as a rectifier. The rectifier means you can convert these AC waveforms, AC power, AC current, or whatever the thing to the DC. Now, why do we need DC ones? Most of the electronic circuits, they are working with DC voltages and low DC voltages, but the reduction of the voltage is not doing by the diodes, but the conversion of this AC to DC will be done by the diodes. When we do this conversion AC to DC, then we say it's not diode, it's a rectifier. Just name change. Okay, then when we consider this, now we have diodes. You know what diode is. Okay, when you consider the applications, now we can say diode is a rectifier. Okay, it's doing this AC to DC conversion. Okay, then the other type, then not only rectifiers, that we have different type of diodes. Okay, then first, a different type of diode is a very common one, very popular one. They are LEDs. These light emitting diodes. The light emitting diode. I think you know this. This is a very popular one. Everywhere you can see light emitting diodes. The LEDs. That the earlier days that we didn't see that much of LEDs there. Okay, sorry. Okay, now you can see. So that I have shared the new video. Okay. Then LED is a very common one, very popular one, and we are the early days that we use these LEDs for the indicators. When you have a power supply, when you have your TV or monitor or mobile phone or whatever the thing, then to show that it's in one mode, the power is there. That to show those things that as an indicator, we use LED. The small indicator will be there. It always it's on. Then you can see the power is there or the device is working like that. Okay, but later on the LEDs, we use LEDs for different type of purposes. For example, these LEDs we use for TV or maybe monitor screens. Okay, and to make monitor screens or TV screens, actually this should be this is not a normal monitor. This is not a normal TV. And when you consider the large TVs, and we have LED TVs, but normally whatever the thing that we use a laptop for, the desktop for, whatever the thing that we have this 19-inch or the 24-inch like that the monitors. But in addition that you at your home front you may have 32-inch, 42-inch like that, 52-inch like the TVs. But most of those TVs are not LED TVs. Although they have mentioned they are boxes or the manual or whatever the thing, they are LED TVs, but they are not LED TVs. Okay, when you consider that one, that actually here, then how they mention those things, how can they mention this one as an LED TV like this? This is LED. No, they are not LED. But screen is not LED, but how they put this LED TV term there, but to power up to light this screen, to light this LCD screen, but these screens are LCD, liquid crystal, not LEDs. Okay. But how can they put this LED TV or LED monitor over that term there without having any kind of the legal action that anyone can take legal action that they have put their wrong information there, wrong idea there. They have done that one. How can they do to light up this screen? Okay, to light up these screens at the in front of the sorry behind the screen, inside the monitor or TV, they have backlights. Okay, they have backlights. Why do we need backlights? To light up the screen. Then without having a backlight, you can't see anything. Okay, with these backlights, they use LEDs here. Sometimes that you may have experience that your TV is going to that fading away, and it's little by little your color is going down like that. If you have those things that you have to, when you go to the repair shop, they will replace this backlight LEDs, and they are LEDs, and these things are LEDs. These are LEDs. This is backlight LED. Because of this one, they say their TVs and monitors are LED. Okay, but really you have LED TVs also, but today that I think you can't even reach to that one. But earlier also we had LED TVs. Then how they developed this LED TVs? If you consider that one, and this is the same principle they have used in the LCD TV. Also, you have small dots, but here also we have a dot. And with these dots, the picture is forming. Okay, then we can color up the dot in different colors, and at the end, the image will be created. But inside this dot, what they have is we have these 3 LEDs there. First one is red, the other one is green, the other LED is blue. Okay, then inside here, sorry. Inside this dot, we have 3 LEDs. Then making this, turning on these LEDs in different intensities, we can make different colors. But this setup is having with all the dots. They are real LED TVs, but the cost is very high. Okay, I think you have seen that in the maybe in the cities that you have seen LED walls in the maybe. Okay, can you give me a minute? Okay, then like that we can make TV screens, and for this one to make LED and monitor screens that we can use these LEDs. The other one for the lighting applications. For lighting, we use LEDs. Okay. Then the high voltage LEDs are there. Earlier we had a small LEDs, but they don't have much more power there. Only the illumination is limited illumination is there. But now we have high power LEDs. With this high power LEDs, we can do lighting also. So you can see that the color lights and these street lights and all these, and with your home front also, that you may have at the moment you may have used many LED bulbs at your home front also. Okay, that different applications are there, but all these things are diverse. Okay. But it's not like the diodes. That diode LED is having a specific application. That this is the circuit symbol of this LED. To take a light or to turn on this LED, we have to provide certain power. For example, we have to provide this voltage across this one. The forward voltage, I think in the diode, that to turn on this diode, or maybe to send voltage or current through the diode, you need 0.7. But for LEDs, this one is different. Okay. But for the LED, that generally we take this one as 2.2 volts or 2 volts. But depending on the color, the working voltage, the forward voltage is different. But generally, if you provide 2 volts there, you can turn on these LEDs. But especially this red, green, orange, and yellow LEDs. For these LEDs, this voltage is okay. Okay. But when you use blue and white, this is 3 volts. Okay. The normally LED is having a very small voltage, but anyway, that specially developed LEDs are there. They are having higher voltage. 1 watt LED is there. When we combine 1 watt LEDs together, you can make a bulb having 5 watt, 3 watt, 5 watt, 9 watt, 11 watt, like that. Okay. And then if you want to turn on this LED, you have to provide this one. That, for example, that if you have maybe 6 volts battery, here you have 6 volts battery, then how can we turn on this LED? Because this LED wants 2 volts there. Then we have to put a resistor series with the LED. Then we can calculate this one. The normally this LED PF, we can take generally it's 2.2 volts. And when you turn on this, the LED can have the 5 to 30 milliampere current going through that one. Depending on the pass-through current, the LED light intensity will be determined. Okay. Generally, we can take this one as 10 milliampere is very much enough. And if you consider this one as 10 milliampere is going through this LED, then this is R. Across the LED, we can see it should be 2.2 volts should be dropped. Then across the resistor, the balance should be there. Then it should be here 6, then it 3.8 volts. Okay. Then you can calculate this R here. Then you know R should be 3.8 volts divided by 10 milliamp. Okay. Okay. Then we can divide this one, the 3.8 volts. 3.8 volts, then we can convert this one into 0.1 amperes. And 3,800 ohms. Then nearly it's 3,800 ohms, but generally that we don't have that type of resistors there. We have 3.3 kilo ohm resistor, or maybe 3.9 kilo ohm resistor. Those are the resistors in practical we have. You can select either 3.3 K resistor or 3.9 K resistor here. Then if you use 3.3 K resistor, the current will be little bit higher than 10 milliampere. Then LED intensity will be little bit higher. And if you use 3.9 K resistor here, then you will have less brightness than the previous one. Anyway, that for both resistors, if you use both resistors, there is no problem. You can turn on this LED. Sorry. It should be 380. Thank you. 380 ohms. Okay, then if you have 380 ohms, we don't have this figure resistors. In practical, we have only 330 ohm or 390 ohm resistors. Then you can select either one. Okay, that's okay. Like that, you can calculate that what type of resistor you have to use. But here in this case, that if you want, you can put another resistor in series, another LED in series like that. Okay, we can change this diagram here. At the same time, but here you have 6 volts battery. But you want to have more LEDs. If you have one LED, sometimes if it is not enough, then you can put 2 LEDs there and resistor. And this time you can calculate this resistor value here, 6 volts. And across these two ones that we have how many voltages, and 2.2, 2.2, this is 4.4 volts drop is there. Across the resistor, how much it is? It's 1.6 volts. Now you can calculate that this time also that you can put this current here. It's 10 milliampere going on this one. But if you need much more intensity, much more light intensity from these LEDs, these ones, and you can increase the current, maybe 20 milliampere, 15 milliampere like that. But for the safe side, 10 milliampere is much more enough. Okay. Now also you can calculate this resistor value here. R is 1.6 volts again. 0.1 ampere, then it's 160 ohms. Okay. Likewise, you can calculate how much of resistance you need. Then you matching this one with the market available resistor. You can select nearest resistor there. In practical, But for the theoretical calculation at your examination, if I ask this question, then you have to have this theoretical calculation like this. But when you do this one practically, when you go to the market, you cannot find 160 ohm resistor there. Then you have to take a nearest resistor value. Okay, that's how that we can turn on these LEDs, and for this high power LEDs that we have different drivers there. We don't use these resistors to and this battery combination to power up high voltage LEDs. But in the normal LEDs, this simple mechanism, this simple calculation, that is enough to select a suitable resistor, and you can turn on LED. Okay, that's about LEDs, and this is a special type of diode there, as I mentioned. Another special type of diode is Zener diode. Okay, the next one we are going to discuss is Zener diode. Okay, and you may remember that when we have a diode like this, okay, we can apply a battery like this, and here we have this forward voltage. It may be 0.7 volts or 0.3 volts, depending on the materials we have used to make this diode. And likewise, and you may remember the VI characteristic curve of this diode. Okay. This is the voltage axis, and along this voltage axis, we can apply the negative side and positive side here, and we can check the current going through this one. And this is the current going through this. And when you apply initially 0 volts and 0.1 volts, 0.2 volts like that, diode is not conducting. It's not allowing to go current through it. But after applying certain voltage here, it start conducting. Okay. Like this. In the forward voltage side, it has this one. Then we say this is VF. It's nearly 0.7 volts for silicon. Okay. And the reverse side, when you reverse this voltage, reverse polarity, the diode is not allowing to go to the current through it. But after increasing this reverse polar voltage to a certain limit, the diode will be damaged. Then after that, the large amount of current can go through it, but then diode will not come back. It will be destroyed. It will be damaged. Okay. Then we say this is VR, and after this VR voltage, diode could not be recovered, and it will be damaged. It will be burned. But especially the Zener diodes are used. The Zener diodes are developed to use in this region. Okay. In other words, you can apply Zener to the Zener diode the reverse voltage, and after that, after certain Zener the voltage, then the current is start going through it. Current is going through it, but then it's not like normal diode. Diode will not be damaged. Diode can come back to the normal state. Okay. Then if it is Zener diode, the symbol is a little bit different. It's not like previous diode. Now we have a different symbol. Sun. This is normal diode, and this is Zener diode. Okay. Then how can we use Zener diode? So this one, with this, we can draw a different characteristic curve for this one. This is the voltage axis, and this is our current axis. And Zener diode also behaving like a normal diode. And it has this forward, this one, this V forward also, it behave like a normal diode. But at certain voltage, when we reverse this one, it start conducting at a certain negative voltage point. And we say this point is V Zener voltage. Okay. Then Zener voltage, Zener diode. This one, we mentioned two things. For example, if you mention, if you have that with the Zener diode, if you have these 2 points mentioned with this one, maybe this. These are the two quick parameters you can see with the Zener diode. What is this? This is the Zener voltage. At minus 5.3, it starts conducting reverse side. But for the forward side, when you forward bias the diode, when you forward bias the Zener diode, it's behaving like a normal diode. But you can reverse bias the Zener diode, and you can use this reverse bias mode to useful action. But when you reverse bias the Zener diode, at a certain voltage, it starts conducting. And after reducing that voltage, it can come back and it can behave like a normal. Then that particular voltage point, we say it's a Zener voltage point. This is V Zener voltage. This is Zener voltage point. And especially when you have the diode, Zener diode data sheet, they have mentioned this one. This is Zener voltage. And what is this 0.5 volt? Okay. When you apply this one, for example, we can connect this Zener diode here. This is plus, minus. Here we have a resistor, and this is our Zener diode. Okay, that we can have this one. We can have the battery voltages. You can see that we applied this diode in a. Sorry. Now we reverse bias the positive voltage has come here, but it's applied to the cathode terminal. Then diode is reverse biased. But after applying this one, then assume that this Zener voltage is 5.3 volts with the. If it is 5.3 volts across this one, the 5.3 volts, the Zener start conducting. Then this forward current will be there. Okay. Then this 0.5, what meaning is? This. You can have this reverse current through a Zener diode, but your limitation is this. Then I can be determined 0.5 watt divided by 5.3 volts. Then nearly 94 milliamperes we can send through this diode. Is it okay? Can take this one, then 0.5 divide by 5.3. Yes, it's 94 milliamperes. Okay, that much of current we can send through the diode. Okay, then this is reverse current. Because this current is the reverse current, then we can say this is reverse current, and this is VZ. The reason that we say is reverse current by that we have applied this reverse bias voltage to the Zener diode. Okay, when we reverse bias the Zener diode, then only start conducting in reverse mode, and the Zener voltage will be applied in the reverse mode, reverse bias mode. Then at the Zener, the reverse bias mode, certain current is going through the Zener diode, we can call it a reverse current. It's not a forward current, but you can use this Zener diode in the forward bias mode also. Then the different current will be here. That is reverse current. That is not reverse current. It should be forward current. Is it okay? Okay, then we can have a small question regarding this one. Let me. Then this one we can take. We said 6.8 volts. Then the voltage is 1 watt. Okay. Then there should be current, and you have to find this I and R here. Okay. Let me do a small change here. You can put resistor here. And Can you do this calculation? Okay, then how can we do this calculation? I think it's now here across the Zener diode. What is the voltage here? It's 6.8 volts. But you know that Zener voltage with this, we can find this current. Then we have 1 watt and 6.8 volts Zener voltage. Then I said. Okay. Then I said equals 1 divided by 6.8. Then it's nearly 147 milliamperes. Okay. Then now here across this resistor, this is VR. Then how can we find the resistor value here? Then you know VR equals IZ into R. How much VR? There we have 12 volts. Then VR should be, this is 5.2 volts. IZ is 147 milliampere. Then R. Then you can find R 5.2 volts divided by 1.47 amperes. Then it's 35.3 ohms. Is it okay? Is it okay? Okay, then if it's okay, then we can discuss about some kind of Zener diode applications. Okay. Then first application is voltage regulator. What does it mean by voltage regulator? What actually voltage regulator does? Then why do we need a voltage regulator? Okay, then for example, assume that you are providing power to some kind of DC circuit. Okay, this is your DC circuit. And actually DC circuit means that any kind of DC electronic circuit, it means inside you can consider we have a some kind of variable resistor there. Okay, this is our electronic circuit you can consider, but this may be a variable resistor. Why I am telling this variable resistor? Depending on the work will be carried out inside the circuit, the load current may be varied. For example, assume that you are listening to a radio. Then you are powering up the radio by a battery. Then when you have tuned to a certain kind of radio station, then you can listen to a song or whatever thing the radio, you can listen to radio channel. Okay, but during that time that your radio is taking some kind of current from the circuit. Okay. Then it's taking some kind of current from the circuit. Okay, then it's R1 value, R value may be 1. Then I1 may be there. But sometimes that the volume of this the radio coming out from as a volume, the volume is not enough to listen to that music. Then you are increasing the volume. Increasing the volume means inside the radio, the much more power is used. Earlier, it's using some kind of power, the moderate power. But you are increasing the volume means that you need much more, that the voice is coming, that much more the powerful one you need. Then radio has to provide the loud noise there. To provide that loud noise, it's expecting some kind of power, additional power from the battery, from the power supply. You can consider this time it's a different resistor value. Then because of this different resistor value, now current has changed to the different current. Now from the circuit, you are taking much more current to provide much more power to the output. And what I want to say here is that depending on the work done by this electronic circuit, time to time, then this load current will be varied. If the circuit is taking less load, the less current will be taken from the battery. If the power is taken by the circuit is a much more higher power it's using at the moment, then it's drawing higher current from the battery. Depending on the resistor value here, this current may be varied. But if it is battery, if it is battery 6 volts or 12 volts battery, this will not be a problem then throughout the battery, but sometimes throughout the certain time that battery voltage may be there if the current is in the manageable region. The battery voltage is not going to drop out. But assume that depending on this power supply, sometimes your power supply is providing 12 volts at 1 amp. This may be the power supply specification. But if you take much more current, depending on the amount of current you are taking from the power supply, okay, this voltage may be dropped. Okay, this voltage may be dropped because of that during that time. But here, this is your circuit. This is the load. Load mean our circuit. This is the battery. Okay, this is the current we are drawing from the battery power supply. Okay, when you take much more current, sometimes the battery voltage, the power supply voltage may be reduced. Why? Here we have some kind of power. Here we have 12 volts into 1 ampere. It's 12 watts are there. This one is fixed. Okay. If you draw more current, the voltage will be reduced. If you take less current, sometimes the voltage value may be there. But again, the load can see it's receiving different voltages at time to time, depending on the amount of current it's taken from the power supply. But then the load is not receiving the fixed amount of voltage to these two inputs. But here the load is expecting 12 volts across the load. Okay, that's what load is expecting. But depending on the amount of current load is taking, this voltage may be varied. Then this circuit, this load will not be working properly. Why? It's receiving the varying voltage. Because of this reason, then voltage regulate. This voltage regulator circuit is needed. Now this voltage regulator is needed. Why? The regulated voltage, the voltage regulator can regulate the voltage across this power supply. Then power supply is having voltage regulator. Then it will not be a problem to the load. Okay, this will be much more comprehensive if I draw your previous diagram again. You may remember that you have a transformer here. And here we have a diode bridge. And bridge is connected to this one. And from the bridge, we have this type of voltage, but in the we have put a capacitor here to have a smooth voltage here. But you know that at this point, what type of voltages here we have? Very high voltages. In this here we have very small voltages, but at this point we have voltages like this. This is the output voltage at this point. Okay, but you know that if you connect a resistor, and your resistor is a variable resistor like our normal load is taken, then depending on this resistor, the amount of current will be determined. Depending on this resistor, I can be determined. The I can be varied when your load resistor is varied. But here, when you take much more current, what about this ripple? Okay, for For high currents, the ripple may be increased like that. But for low currents, low I, ripple may be something like this. Why? When you take high current from this one, this capacitor can provide that the balance voltage to the circuit. When the voltage is not provided by the transformer side, there's a bridge rectifier side, then capacitor has to provide power. But when you take much more high currents, the capacitor will be discharged very quick. Then ripple will be increased. But when you take low currents, what about the final voltage here? Okay, then if you take the average voltage here, we average here, when you consider we average voltage, this we average 1 and we average 2 when we compare this one. We average 1 will be high when you compare to we average 2. Why? Depending on the load resistor, the load current will be varied. Because of this current is varying, output voltage, the ripple voltage and everything will be varied. As a result, this output voltage, the circuit voltage will be varied. But that's what I explained here. This circuit is receiving different voltages from the source. It's not good for this load. Here it's a resistor, there is no problem. But if it is a circuit like this, if it is a circuit, okay, this circuit is expecting almost the fixed amount of voltage throughout the period for proper function. But now you can see load is requesting sometimes much more current, then voltage will be dropped. Then load is sometimes taking only less current, then voltage will be increased. Then that regulation is not there. Because of that, we need voltage regulator. Okay. Then if we have voltage regulator, all the time we have fixed voltage across this load. That's what we need, a voltage regulator. Then how can we put this voltage regulator? Where can we put this voltage regulator? Okay, here if we put, this is point A, and if this is point B, then where can we put this voltage regulator? And this is point A, and this is point B. After that, we need this voltage regulator. This is voltage regulator. Circuit. Then after that, you can connect your load circuit here. This is your load circuit, and this is your load. After that, you can connect your load here. Load may be a variable resistor inside, we can consider like that. Then here, now what about the voltage regulator output? Then at point C and D, here, we have regulated voltage from the voltage regulator. But here, this voltage is voltage. This is unregulated voltage. Unregulated voltage can be varied, but regulated voltage cannot be varied. For a certain current range, this voltage regulator can provide regulated voltage. It will not be varied depending on the current taken by the load. Okay. Then hereafter, in between that, when you have a small circuit, when you have a normal circuit, but we don't put a voltage regulator here. Sorry. We don't put voltage regulator here. But if you have connected the sensible voltage, sensitive load here, your sensitive circuit will not be properly functioning if you provide variable voltage. If your load voltage is, the power supply voltage is not regulated, it will be greatly affected to the load. Because of that, we need a voltage. Okay, I am telling these things that are taking much more time to you to tell, to understand, to say the importance of this voltage regulator having, before you supply the supply voltage to a circuit. For example, your commercial power supply power outlet may be there, and you can take a normal power pack from the local market. And in the local market power pack, it mentioned that 6 volts, 1 ampere current is there. But assuming that you are connecting your, for example, that you have electronic organ, assume that like that. In the electronic organ, it's mentioned that 12 volts, 1 ampere power supply is required. Then you can go to the market and very cheap power packs are available. It's mentioned in the power pack, output is 12 volts, 1 amp. Okay, you can see that. Okay, exactly matched what my organ is requesting is 12 volts, 1 amp. But what the power supply is mentioned, 12 volts, 1 amp. Okay, you think that it's very good now, both things are matched. Then you can take that one and put it to the wall outlet, and you can provide power to the electronic organ. Now, electronic organ is a very sensitive device. Now, when you are playing that one, you need much more volume. Then you increase the volume, and while playing, you are increasing the volume. Then your organ is taking much more current from the power supply. But your power supply is very cheap one. There is no inside voltage regulator. Because of that, it cannot provide regulated 12 volts output all the time. Depending on the amount of current your organ is taking, voltage regulate your power supply is reducing the voltage. Much more current taking, less voltage. You are taking less current, high voltage. Like that, you have different voltage providing to electronic organ time to time, depending on the current you are taking. It's not good for your organ. Most of the time, your organ will be damaged. Okay. Then what do you need? You can go to the market again. You can check different power supplies. You can see 12 volts 1 ampere power supply is available, maybe 1,250 rupees. But different power supplies are available. It's also mentioned 12 volts 1 ampere, but that power supply may be cost as 3,500. But what is the difference between this 3,500 12 volts 1 ampere power supply and same type of things? It's mentioned in the cheap one also. It's mentioned 12 volts 1 ampere and 1,250. Definitely, most of the people they will buy the cheaper one. Why? All the specification they mention is, but there the high price one, it's having inside voltage regulator, and it can provide regulated voltage. And when you take 1 ampere maximum current, still it can provide 12 volts. When you take 100 milliampere current from the power supply, still it can provide 12 volts. Otherwise, when the amount of current you are taking from the power supply, your output voltage will be varied. Depending on the current, output voltage will be varied. Okay, but if you have voltage regulator, you will not have that problem. Did you understand the importance of having voltage regulator there? Still, we didn't come to the subject. Actually, we are discussing about the Zener diode voltage, but still we are not. Still, we didn't come to that point. We are discussing about the importance of voltage regulator, and we are trying to understand how it is important and why do we need that one, and what is the function of this voltage regulator. That's what we have discussed. So, is it okay? Is it clear? Okay, Lindsay, thank you. Yeah, please that I'm receiving time to time less number of feedbacks, but anyhow that you are there to provide. Yeah, Didula is asking, is the power of the voltage source constant even through voltage and current can vary depending on the load? The power of the voltage source constant even through voltage and current can vary depending. Yes, Nidula, actually that if you are taking power from a that regulated power supply, whatever the amount of current you are taking from the regulated power supply, it doesn't matter throughout the period, throughout the time, throughout the period, that whatever the thing, if it is in the manageable region of that voltage regulator, it can provide regulated voltage irrespective of what amount of current you are taking from it. Okay. Now we can try to understand this Senadiode voltage regulator, then you will have some kind of idea about this. Okay. Okay. Shall we do that? Is it okay? All of you have understood that how important this voltage regulator is? Okay. Then from this side, I draw only mention this is supply voltage. Okay. This is supply voltage. It may be coming from a transformer type full wave rectifier, or it may be as normal your power, whatever the thing that we don't know, it's a voltage, supply voltage, and it's coming from this end, and from this point onwards, we are drawing our regulator circuit. This is center voltage regulator.
This one is not asking the question, but I want to know.
Okay. Then we can take this is Vs supply voltage. Then we can take this as Rs. Then this is Zener diode. The voltage, Zener voltage is, we can take it as Vz. And we have connected our load here. It's anyway variable resistor. We can say it's RL is our load. Okay, we can take this, our Zener diode. Then V Z is 5 volts and voltage is 1 watt. Then put in this Zener diode 5 volts means, and during its Zener region, and when the diode is in that, okay, we can take this. This is plus 0 volts. And then we are expecting to receive 5 volts to this load. That's why we have selected Zener diode as the 5-volt Zener. Our Zener diode is a 5-volt Zener, but we don't have actual that. We'll come to that one later. For the moment, you can assume that the diode Zener voltage is 5 volts and its voltage is 1. Okay, then we can mark the currents here, and this is IS, supply current coming through is, and this is IZ, current going through the Zener diode, and this is load current IL. Okay, we can write our first equation here. That is a very simple one. Then IS equals IZ plus IL. Is it okay? It's a normal Kirchhoff law. This total outgoing currents are equal to total incoming currents. IS equals to IL plus IZ. Okay, now assume that we have this electronic circuit here. This is kind of electronic circuit, and this is our load. Okay, we can assume that during certain time this load can be varied, but we have to calculate how much of current we can handle this one. Okay, and this load current can be varied. Why? This RL is varying, because of that IL will be varied. Depending on the RL, IL will be varied. Okay. At the maximum RL value, when the RL is maximum, you can have the minimum. When RL is very high, as a result, what about IL? If RL is very high, what about IL? IL is having low value. If RL is reducing, then IL will be having higher values. Is it okay? It's a normal thing. You can understand this one well. If the resistor is very high, less current is going through it. The resistor is very low, high current is going through it. Okay. Okay. Depending in that one, that assume that RL will be 1 kilo ohm. That is the maximum value of RL. This is maximum RL. When the maximum RL is there, we can calculate what type of current we can take from that. Okay. For the moment, we can take the power supply voltage. We can take this VS as 12 volts. Okay, then we can find VR is Vs minus Vz. Vs is plus 12 volts. Vz is 5 volts. Then across the resistor, we have 7 volts. There. 7 volts drop is there. Okay. Then we can find how much of current then Zener diode can handle. The Zener diode maximum current, how much of maximum Zener current can Zener diode, how much of maximum current it can handle. Okay. Then I set maximum value. The Zener current can handle. It's how much watt? 1 watt divided by 5 volts. Okay. It's nearly 200 milliampere current can take. Okay. The maximum I set current is 200 milliamp. The Zener can handle maximum 200 milliampere current across through it. Then because of that, you know that 400 milliampere current can send Zener diode. That is the maximum Zener current it can handle. You can find the minimum value for the series resistor Rs. Okay. Now you know the 7 volts across this resistor. We have 7 volts. Then to find Rs, we have 7 volts divided by 200 milliampere. Then this is 35 ohms. Okay. Then we know that here we can put 35 ohm resistor there. This is one important point. We have to put 35 ohm resistor there, and we have calculated that how much of Zener current it can handle, 200 milliampere. This one. Okay, then now with this all these figures we know that, but during that time, you know that maximum load is here 1 kilowatt, 1 kilo ohms. Okay, then 1 kilo ohm resistor is here. Because of that 1 kilo ohm resistor is here on the load side. This is RL is 1 kilo ohm. Then we can find IL current during that time. Then 5 volts is there. Then 1000 ohms. Okay. How much of current it can take? then it's 5 milliampere current it can take. Then IL will be 5 milliampere. IL will be 5 milliampere. And when the RL is 1 kilo ohm, IL will be 5 milliampere. Okay, when RL is 1 kilo ohm, IL will be 5 milliampere. Then during that time, how much I said? I said is the total current we can take from the load. The power supply is 200 milliampere. This is 200 milliampere we can take from this one. But here from this side we can take 200 milliampere. But now we will send 5 milliampere across the load and the balance across the Zener diode. But Zener diode is something like that. You can see. Here, the current may be that, see this one here, current may be certain kind of value here, but Zener voltage is fixed. This may be the less current, but Zener current may be very high value. Still the Zener voltage, Zener is maintained the same voltage across the Zener diode. Because of that, current can be varied to the different values, but still the Zener voltage may not be varied. Because of that, during that time, Zener current is IZ will be IS minus IL. Then we have 200 milliampere there. And now we have 5 milliampere. Then 195 milliampere current going through Zener diode when the load side resistor is 1 kilo. Okay. Now assume that RL is going to decrease. If RL is decreasing, okay, if RL is decreasing, then IL will be a different value. IL will be a different value. Then, for example, you can say the IL will be 10 milliampere. IL will be 10 milliampere. Then, if IL is 10 milliampere, IZ may be 190 during that. But IZ can be changed. Okay, but we can see this one. This is our graph. This is Zener diode this way. Keeping here, we said 5 volts. And during that time, the maximum current it can handle, it may be here, is 200 millivolt. But it can be where it can be come up to here also. We have to find that on the exact figure. But sometimes the 10 milliampere current, still IZ can be 10 milliampere, voltage is 5 volts. Then IZ maximum it may be 200 milliampere. This maximum is coming because of 1 watt. Okay. But less than 200 milliampere, it can be varied up to 10 milliampere or 0 milliampere, not 0 exactly, but it may be different value. It can vary. The current can be varied during this huge range. But this huge range, IL can be varied. IL can be go from 5 milliampere to 190 milliampere. Then during that time, IZ will be varied from 190 milliamperes to 10 milliampere. Did you understand that one? Then how they can regulate this one? Then when the load is varying, this one, RL can be varied. RL can be increased. Then if RL be increased, then as a result, IL will be decreased. When the IL will be decreased or increased, as a result, IZ can be increased. The reverse also same. When the RL is decreasing, IL is increasing. When IL is increasing, IZ is decreasing. In both way, it's okay. Then like that, Zener is working as a voltage regulator. Vidula is asking, how did you decide 200 milliampere through RS? Okay, Vidula, it's a great question. He is asking that how can I decide RS? Okay, assume that then this RL is not taking any current. Load is not taking any current. Okay. During that time, what is the path this current can go? Only through Zener diode. Assume that RL is 0. Sorry, RL is maximum. RL is infinite resistance is there. Or maybe you can assume that RL is not connected. Or if the RL is not connected, let me draw it again. Okay, without drawing, shall we copy it? Okay. This is the normal situation. If no load connected. No load connected means we don't have this. Okay. Then during that time, what is IL? IL is 0. Okay. Then during that time, Vidula, this total IS current is going through Zener diode. But Zener can handle only up to 1 volt. Okay. Zener can handle only up to 1 volt, maintaining 5 volts across it. Then we have to find how much of maximum current Zener can handle. That's why we find this IZ value. This IZ value that is 1 watt divided by VZ. Then 1 watt divided by 5 volts, 200 milliampere. Okay. Then IZ maximum, this is IZ max. This is the current Zener can handle without damaging it. The safe side, this is the maximum current. Then this current, because during that time, IS, the supply is providing certain current during that according to the setup. But anyhow, we haven't connected the load. And load is not taking, we can assume that we have connected the load, but load is not taking any current. During that time, the Zener has to handle everything. Zener has to take the entire current and it has to draw it through it. Okay. Then 200 maximum current is going through Zener. Then we have to find, to be in the safe side, we have to find RS value. Okay. That's why we put this calculation here. Then RS we can find, because across the resistor, we have 7 volts, but we put this maximum 200 milliampere current there to find this RS. That's how we came into 35 ohms. Then we have to put at least 35 ohm resistor here to this RS to protect the Zener diode. If you don't put this 35 ohm resistor here, the maximum current can go through it, the Zener diode, more than 200 milliampere, then Zener diode will be damaged. To protect the Zener diode, we have to find the maximum Zener current. According to the maximum Zener current, we have to find RS resistor. Is it okay? Vidula? Okay, any question from others? Any question? The maximum Senna current that it can handle can be always taken as a constant value. Maximum Senna current that it can handle can be always. Maximum Senna current means such trigger that whatever the thing that the load is not connected, because that if the load is connected, load can take some current. Then there is no problem. But when the load is not connected or the load is not taking current, then IL will be 0. During that time, Senna has to handle everything. Senna has to handle the maximum current. Then we can calculate maximum current at that point. Taking that IL is 0, that everything will be going through the Senna diode, then you can, you know the wattage of the Senna, then you can calculate Senna current, maximum Senna current. Then when you know the maximum Senna current, you know that we have to put a resistor in series. Then series resistor can be calculated considering the maximum Senna current. The meaning is we are not allowing current beyond 200 milliamp. If the current is 200 milliampere or less, the Senna is protected. If current is going to be increased at 200, more than 200 milliampere current, it's fine when the load is connected. But when the load is not there, all the current going through Senna diode, then we have to protect the Senna diode. Then protection is below 200 milliamp. Okay. Then after that, you can connect any load here. But you can find, can you find that maximum maximum resistance for the load? We have this as, we have taken as 1 kilo. What is the minimum load resistance it can have? Okay. To do that, we need this information. Without having this information, we can't find it. We need that minimum value of Senna current it can handle. Because after that, the Senna action will not be there. Then if you know this minimum value, we can take this one as IZ. Then you can take IZ plus IL, it should be IS. Okay, in this case, if this is in this case, if it is 10 milliampere, and then IL will be 190 milliamp, because this total current is 200 milliamp. Because that we have total 200 milliampere total current. Because of that, IS can be reduced up to 10 milliampere. The meaning is load current can be increased up to 190 milliamp. Then we should have that information. Otherwise, we can't do this calculation. Is it okay? Yeah, any question? I think if you ask questions that all others are benefited. This is not a very difficult thing, biggest thing. It's a very simple thing. Zener diode voltage regulator is a very simple thing, but you have to understand what is doing there, what is happening there. If you understand this diagram well, then very simple calculation actually. What we have to do, and we have to understand that depending on the load resistance variation, we have to understand that how much of what type of Zener diode we have to put here. When you selected this Zener diode, then we have to calculate this RS resistance. In this question, that's what we have to consider. All the time, the circuit is this very simple circuit. One Zener diode, one series resistor, and from the junction, we can take the regulated voltage. But regulation is there for a certain range of current. We have to find that current and the series resistance. That's what. Sitra, yes. Sitra, that you asked me, that means that the load is not there. It's an I. Yes. Zener maximum current is, we can calculate like here. The maximum Zener current. I said maximum you can calculate when the load is not connected. Is it okay? Okay, I'll provide some kind of questions to you. Maybe. Okay, then you can practice it later on. Anything else? Any other question? Okay, if you don't have any question, then we can wind up the class today for the moment. Tomorrow evening we can meet again. Until that, thank you very much for your time. Thank you very much for your participation. And I'll expect much more questions tomorrow. You can come up with a different type of questions. Then all will be benefited. Okay, thank you very much. We can finish the class today. Until that, have a very good time. Thank you very much.
Thank you, sir.